Okej. Nie lubię słuchać swojego głosu. W każdym razie, zwykle ja mówię, że jestem z internetu, bo zwykle mam daleko prezentację i nikt nie wie, gdzie jest Poznań. Ale teraz mogę powiedzieć, że mieszkam w Poznaniu, przyjedźcie, jest fajnie. Natomiast będę mówił po angielsku, bo po polsku umiem tylko narzekać. A i to nie to o komputerach, bo wtedy sobie nie radzę po polsku. Także no, jedziemy. Dzisiaj będziemy mówić o tym, że Python jest wolny i co możemy z tym zrobić. Zaczniemy od tego, dlaczego jest wolny i co to dokładnie oznacza. Okej, to jest chyba ten moment, że muszę zmienić na angielski. Then we're going to talk about ways to make it better. There's quite a few of them already, even without mentioning type annotations or mypyc specifically. But we will talk about how type annotations can help us and how this is not, in fact, an obvious thing to do. But mypyc does let us do it, so we're going to be talking about that. And then we're going to finish with a question I've been having like a lot when mentioning using type annotations to make stuff faster, like why don't you just use PyPy? So we're going to be talking about this too. So let's start at the very beginning. Python is good enough. It's not fast, it's not super slow, but it's good enough. It's the second best language in any case, in any use case. You can use it for pretty much anything, but everybody just says it's good enough. What does that mean? Well, Python is pretty good at networking. If you have a networking server like with UV loop for async IO or the twisted reactor that's written in C, the throughput you can get from it is pretty much comparable to Java web servers or to servers written in Go and so on and so on. So to solutions that were made pretty much with this use case in mind. So Python can be fast, but when we are talking about pure computational speed of a single thread just crunching numbers, well, we're not in the same ballpark anymore. Python can be pretty slow for this. So in particular, if you're doing signal processing, right? So there's a bunch of numbers that we're getting from somewhere and we have to do some computation on it. We're not doing so well anymore. This is from some paper on like FM synthesis that I used to do FM synthesis in Python that I prototyped to later implement FM synthesis in a synthesizer for Polyend, a Polish company based in Olsztyn that does musical instruments. The actual implementation was later in C++, but prototyping was in Python. But you know, kind of musical instruments aside, data processing is any kind of data, and in particular the interesting ones are like video, right? So you have color grading, you have all sorts of visual effects, and you know, kind of mixing formats, and you know, making multi-scene kind of recordings, sync and whatnot. A lot of this is now accelerated with GPUs, but it is still a CPU-bound workload most of all. So all those use cases, Python is not doing so great at them. And in particular, yeah, like this is the Yamaha DX7, something that like you probably heard, like, you know music that this rings in it, like even if you don't know how the, like what this device is, like you've heard it, like Whitney Houston, you know, kind of to Trent Reznor, like it's the sound of the 80s. So it was released in 1983. And yet, when I was trying to recreate how this sounds in pure Python in 2020, using a topped-off Intel i7 MacBook Pro, I could not match the performance of this device, like not even like half of it, right? Like this uses dedicated, you know, chips for this computation, but it was still disappointing to me that, you know, while I could do some of it, I could achieve like 5 notes of polyphony. This thing has 16, you know, and it was released 30 years ago. So what can we do? well, we can admit that Python is kind of slow, not for the use cases that allow us to go with concurrency, so dealing with many things at once, like web servers, and not even for like doing many things at once, so like parallelism, where multiprocessing or async IO or a bunch of other schemes can mostly work around the GIL, and you can kind of make do with what Python provides. But for pure computational performance on a single thread, well, we're not doing so well. But why is it? Like, why is Python slow for this particular use case? Well, because it has a lot, and I mean a lot of indirection. In particular, we can ask NumPy people, so the authors of like one of the most known and widely used libraries for this programming language, what do they think about performance in Python? And they have this page in their docs that says, while Python is a great language and a pleasure to code in, its dynamic nature results in overhead that can cause some code to be up to 100 times slower than equivalent code written in static compiled languages. Well, 100 times slower is a lot. So if you look at a simple call to a method on a class, like say datetime.date.today, in fact, we have so many levels of indirection there. Like, first of all, we have to find what the datetime name is. So Python is going to look for it in locals, then it's not going to find it, so it's going to be looking for it in globals. Oh, it's there. So it's going to look what that name entails. It's some pointer to some Py object in memory, so we're fetching it back. And now, oh, it's some Py object, so we have to ask it using getAttr, because maybe the .date attribute is on an instance, or maybe it's on a class, or maybe it's totally dynamic and it doesn't really exist, but our implementation will just give it just in time. So you need to use the getAttr functionality for this. While we have this, we take this new object, and again, it's just a pointer. We have to go to memory, find it, fetch it back. And we do the same thing for date, where we want to fetch the today attribute. It's callable, it's a method, but first we need to fetch whatever it is, because it might be just a function slapped on some instance, or it can be some method, or maybe it's a modified method, like a static method or a class method or whatever else. So finally we have this object, or we fetch it for memory too, and we can call it. But we still have to have some indirection there. Instead of just doing like a C-level call, we use dunder call, because maybe this is an object in fact, and it has some more customization in it. So this very, very simple operation that you would not spend a second reading it if you saw this code somewhere in your program, like has like complexity that is like 10 to maybe 20 times larger than the equivalent in C++, which does pretty much all this resolution at compile time, and later on it just looks at a place in memory, it just changes the program pointer and just goes from there. It's very simple compared to what we have. But thanks to this, we have amazing capabilities in Python, right? Like, you have all this runtime introspection that you can use to, kind of see what attributes are there on an object, to learn about a new code base just using a REPL or IPython or, a notebook or whatever else. And this functionality is very useful for debugging as well, right? You can just put a breakpoint, and then when you actually use PDB, you can just read all the locals that you have in a particular point. You can change the locals. You can execute any code you want. You can import new code. So parts of this is possible in other programming languages, but not nearly to the same extent, where you can really just change behavior of your program and just import an entirely new thing right now while debugging. So this is great, but it is problematic because of performance. Things are getting better though, and this is kind of amazing that, even though the core of Python is about being dynamic and kind of introspectable at runtime, like we are able to make it faster without forcing you to change your code. So in 3.11, you're already going to see performance differences, like depending on your workload, like from 10% to 50% faster. Like the benchmarks that we see right now are pretty kind of, well, optimistic. Like they look pretty good. And in particular, like in the what's new functionality, like the what's new page for 3.11, like there's quite a lot of detail on like what we're gonna do here. And how the faster Python team at Microsoft that Guido works for right now, like, is doing this full time. So this is pretty much like the focus of the core team at the moment. In particular, the specializing adaptive interpreter we're going to cover a little later on. But now let's go back to this NumPy thing where they're like, okay, things are pretty dire. We are 100 times as slow sometimes. So the things that the Microsoft team works on at the moment will give you 25%, right? Like if what you need is 100 times more performance, well, a better Python interpreter will just not be able to fix this, because this is really like a paradigm difference. So what can you do if you need this performance? What you can do is just use a different language, right? Like, oh, one of the most common needs is to call out from Python code to a fast machine code routine. And the NumPy people later on this page just list a bunch of things that they think you should be using. I agree with some of it, I disagree with some of it, so let's go with my list instead. So if you know another programming language, things are kind of all out there for you. You can just write a C extension, like, oh, okay, the default thing that the docs still advise you to do. I would advise you against just writing C extensions directly for Python, because it's so complicated that even core developers cannot do it right. In fact, we have a build bot, so CI, that does nightly builds with additional time-consuming checks to see whether we didn't do reference counting wrong, causing memory leaks. Because kind of if you count the references wrong and you just decrease them too much, like you're gonna get a seg fault. This is terrible, obviously, because it's not a nice exception you can recover from. It's a segmentation fault. Your interpreter crashed, but at least we see this. If you have a memory leak, well, like if it's a pretty minor one, it's going to take a while until your process crashes, because I don't know, like it no longer fits the container limits that you set for memory usage or whatever. So C extensions, not great. It's very complicated to do them. So what do you do instead? Well, Python's docs say, write your performant code in a different language like C. Python is written in C, so obviously this is what they would advise you to do. And now, like, you just build it as a dynamic library that you can later load with C types. Now you have to do some mangling of pointers and strings and numbers that you have in C. This is why this is called C types and not just like some C functions or C callables or whatever, because this is where the most kind of time-consuming adaptations happen. But there's a lot of magic there that makes the resulting code very, very slow on PyPy. So those people said, like, hey, how about we just make a generator of code that allows it to be fast? For example, by just giving it the header file and just parsing the header file and generating the code that we need. So the CPython has code that is pretty similar to C types, like, in the background, but PyPy has very different ones. So CFFI is kind of cool because most of the time you can just copy paste what you put in your .h file and it will automatically generate bindings for you. So if you know C, this is a good solution. But if you know C, you hate C, because C is a terrible language that we created 50 years back, and it served its purpose. You shouldn't write new code in it. Some people would say, oh, like, because we have C++, right? Like, no, like, this is still, no, don't do it. But some people do, like a lot of scientists do, so they use PyBind 11 for it. Like, it's kind of weird because it's a domain-specific language that makes you write C++ that kind of, sorta, if you squint, looks like a Python module. So they're like, oh, look, this is almost Python. It's like, no, not even close, but, kind of it's there. Like, I had to list it because some of you is going to be like, what about PyBind 11? It's there on the list. Let's not talk about it anymore. What you should be using instead at the moment, right? Like, because we are rewriting everything in it, is just to use Rust. And you can, in fact, use Rust now for Python extensions with PyO3 and setup tools Rust, which pretty much gives you the same performance, but removes a lot of issues with memory safety, right? So buffer overflows are somewhere in the ballpark of 2/3 of security vulnerabilities that were reported between 2019 and 2021, as Alex Gaynor, like the co-maintainer of cryptography, the library for Python, says. So, which is why they added Rust as a dependency instead of relying on old C code. So you can do that too. It's good, but then you have to know Rust now. So, okay, like, kind of a big deal. But if you already know Fortran, you can use that instead, you know. So, okay, fine. Like, but all of those kind of assume that, like, if you know another programming language, then you're fine. Then you can make stuff faster. And the last one, which is the weirdest one, is Cython, which is a domain-specific language where you can put Python code, like literal Python code. It's very compatible with Python. And change the file extension to PYX. Boom, now it's being compiled to be just a tiny bit faster. But if you sprinkle some magic specific syntax, like that is just like Cython specific, you can make stuff actually much faster. And Cython is very popular in the data science world. It's very popular for networking code as well, because it lets you write something that actually is close to Python and achieve performance that is close to C. So let's talk about this last one before we get to better solutions, because this is something that really, like, the industry is very heavily using at the moment. So I used to work for EdgeDB, a database startup based in San Francisco right now. They've been in Canada before, but now they all relocated. So like EdgeDB, if you use it, like you probably have some, I don't know, Flask or Fast API app or Django if you don't know better. Like you have something, there's some user code and you call into EdgeDB Python where there's some connection and you make queries. If you make those queries, like you send them over the network, there's some UV loop based network server that just gets those requests and now like compiles your query, handles your schema, because you know EdgeDB is based on like objects and like that have like graph relations between them. But actually like the data layer, the kind of disk block layer is handled by Postgres, because it's kind of done like in 2022 to just rewrite all this knowledge that Postgres has. So EdgeDB just does like a graph database based on set logic on top of PostgreSQL. So again, you have some networking there. And the fun part is that all these critical pieces are written in Cython. They have to be, because otherwise all of this would be so slow that nobody would treat this database seriously. It would just be like a toy concept where, oh, the syntax is nice, but I would never use it. But thanks to using Cython all here, we can actually just, treat it as any other database. In fact, some kinds of queries are much faster in it than with MongoDB, which EdgeDB is very proud of. I'm lying here a little because, as you probably expect, like some parts of it are already being rewritten in Rust, because Rust, so like it's not all red Cython code anymore, but still it was when the project started. So the critical pieces like were enabled by this project. So how does it work? Well, you write your PYX files, you put them in this Cython compiler, but it really transpiles your code to C. We're gonna be looking at a Cython resulting C file in a moment, so just brace for impact already. You can already start thinking about this terrible C code that we're gonna be looking at. And I'm actually very honest, it's gonna be terrible. But it's generated for you, so most of the time you don't really need to look at it for too long. You use a C compiler to compile it to a Python C extension that then you can just import from Python code, and all's good. Everything just looks at it was always written in Python-ish. right? So like inside the EdgeDB code base, this is being used all over the place. If we look at the code base, you're going to be finding some sort of like SO files all over the place. So like those are like Rust ones, but if you just scroll down, like there's gonna be, okay, Rust, more Rust. Oh, finally, yeah, like we have a GraphQL extension, PyX, oh, and a GraphQL rewrite in Rust. Okay, let's go further. Okay, protocol, network protocol, PyX, protocol PyX with PXD, same thing, it's I can include, same syntax. So you have those two files, then they generate a C file that ends up being an SO that you can import, right? Like obviously now they are platform specific SOs, so this one is Darwin, so you can import it on macOS. But maybe just on my macOS, this Apple Silicon based one, not on Intel, you have to compile it again. So all this is kind of, it's an additional step that you need to do to actually build it, but it makes stuff really fast, which is why it's used all over the place. That's the network protocol. There's like server caching of your statements. So like if you execute the same queries, they don't have to be compiled all the time. Like DB views, same thing. Oh, and Postgres connections, obviously, like this connection also has to be very performant. And it generates even the code that doesn't need to be Python. Well, it's still written in Cython, right? Like so Python-like, because it's much more expressive. It just reads much better than writing all this JSON handling that Postgres does have in straight C. That would just be terrible. So like instead it's written all in Cython. It's much more readable and then enables much better testing. So like everybody's pretty happy-ish with Cython for this particular use case. I could go on and I could go on, but like, there was no synthesizer in the slide for a while, so I need to show you some synthesizers. This one is going to be a little more geeky though. This is like a synthesizer module that mixes signals, right? So it mixes 3 monophonic signals in 1, in 2, in 3, and outputs a stereo signal. It's double, but don't worry about it. Like the thing is, there's a stereo signal, so there's like a left speaker and a right speaker signal that is being output. But those 3, in 1, in 2, and 3, each of those is just monophonic. But you can use the panner to just move it left and right in the stereo field, right? So I had to do this thing for the synthesizer I was working on. And you think, well, what can be simpler, right? You get an array of numbers that are monophonic, and you just then like put certain percentage in the left speaker and certain percentage in the right speaker, and you output the multiplexed like stereo array, like 2 lines, right? Well, no, with Cython it's a little more than 2 lines. First of all, you're gonna notice like if you actually make this very fast, like you no longer write defs, you write cpdefs, and you actually have to annotate all your function arguments, but those are not Python type annotations. These are like Cython specific ones, including C types like int32t, right? Like those are not just arbitrary numbers, those are int32t. So they're signed, they're 32 bits long. You need to know everything, like including when you have a loop, you need to tell Cython that this I here is an int32t. If you don't, Cython will happily compile your code and it'll work, but it'll put PyObjects here, which then it has to, pack and unpack all the time with every iteration, so it's going to be very, very slow. If you put this line here saying cdef int32t I, then Cython knows that, okay, we assume that I is always an int32t, so that loop can be very efficiently expressed on the side of C. So like .c file is going to be looking very nice. And finally, this is almost normal Python, except for this C style casting here, which is like super ugly, but you have to do this. So the resulting C code, I cannot show on a single slide because there's megabytes of it, but I'm gonna try anyway. So first of all, like this code really is super long, as you can see, like thousands of lines. And we're in a very high place in the file anyway. but it's because it has those very helpful comments where it says, this is the line that we're translating from Cython. This is super useful because if something works very slow, you can look at the resulting C code, and when you see some wrapping, unwrapping, you're like, oh, like maybe I can tell Cython not to do this by, for example, just specifying that this I has to be an int32t. So this particular line is just this function signature. So like we're defining all sorts of variables, you know, like essentially the function that we're creating here is, you know, having the same kind of arguments. So, you know, kind of, it all makes kind of sense. Like the names are weird, but you need to remember that C has a flat namespace, so Cython has to generate names like, you know, dunder, PYX, whatever, because otherwise they would conflict with other libraries and everything wouldn't work. Going into more interesting places, like, oh, we have now like those weird lines where we have pointers to the short arrays from the array module in Python, which is kind of like NumPy, but like, you know, super basic. So as shorts is literally saying just copy the pointer. So we're just taking this pointer and assigning it to a value, which makes, again, Cython not have to wrap and unwrap values all the time. We can just use this raw mono thing directly. And finally, when we get to this for I in range 1 frames loop, it is a regular for loop from C. Like, this is pretty amazing that we were able to just tell Cython enough that it directly translated this line into this line. Like, you cannot really make this any faster in C. Like, this is what you would write manually as well. Like, this is the sort of computation. And here, like, this weird line with this C casting is pretty much directly being translated to C code, which also is the most efficient thing that you could be doing for this particular use case. So this is pretty cool. You can use this for all sorts of things where you're interacting with some C library, like, you know, I don't know, database driver, or you're doing computation, so you can make stuff really quick. Like NVIDIA is doing this, like, to actually connect to like GPU specific functionality, or on data centers that have specific hardware for machine learning. You know, they use Cython often to deal with that because it allows you knowing a few rules to make stuff really quick. But you also lose a bunch of things, right? First of all, what you lose is the ability to type things on the Python side. So if you're using a type checker, now you have to use like stub files to say, actually, there's some functions in this SO file, because otherwise, like, how would mypy know that this SO file that you imported actually has some importable names? It doesn't know anything about Cython. So you need to write those, and this is kind of annoying. You know, you have to kind of double your effort. This is not great. And it's a way, kind of, to deal with stuff, but like I'm not a fan. You know, you just do it because you have to. For example, CPython rewrites parts of it in C, even if they were in Python originally, for performance all the time. Like here you have like Python 3.7, and ABC was pretty much rewritten in C. It used to be in Python, so it was easy for us to read it and understand it. Now it's less easy for us to read it and understand it because it was rewritten in C for performance. I think it's a bummer. Like to here you see 3.5 where order dict, that is now pretty useless, but like that was re-implemented in C as well. Like you see 3.7 again where async IO, like parts of it were re-implemented in C just to be faster. And okay, that's all good, but you know, C is hard. We already said that, you know, you have security vulnerabilities and you have this reference counting problems where, like, if you just forget one thing, like either it crashes or will just die in an hour with overuse of memory or whatever. So, like, if we don't want to use a different programming language to make stuff faster, could we maybe use type annotations to speed things up? And when we originally wrote PEP 484 to add type annotations to the language, Guido was very against it. Like, he was super focused on making type annotations fix bugs in Python and make code more understandable. He was absolutely not interested in using it at runtime to make things faster, because this is an entirely different problem space and it's not really the same thing, and we were only 3 people. So he was like, no, just let's write that we will never do it. But I was like, no, like even for a poll, this is too negative. How about we write it like this? So I wrote, using type hints for performance optimizations is left as an exercise for the reader. You know, but like he was right in the sense that the types that you use to express your program, right? To explain to other humans what you expect for your function arguments and what the function returns, those are much different from what Cython wanted to make things faster, right? Like those are totally different types. In fact, I had a talk at PyCon just this year, just about this topic. So like if you want to hear more just about that, like there's an entire 45 minutes of me talking just about that. Just the slide that, you know, from that talk that we need for now is this, that when you talk about some sort of thing that has a bunch of strings in it, right? And you're like, give me many strings. You can just say, give me an iterable of string. I don't care if it's a list or it's a set or whatever else. Just give me that. There's a bunch of problems with iterable string, but let's not talk about it right now. Or maybe your API is like, oh, this is some kind of birth date, but it comes from some external JSON, so it can be either a number, because it was somehow encoded, you know, with Unix epoch time, or it's a string, because there's no date times in JSON, or it's none, because this field was just not given. So those are perfectly fine types for your program. Or maybe you just give somebody a tuple of ints and you say there's going to be 1 or more, maybe there's going to be 10, but just ints, but like however many. Those are all perfectly fine types for humans to interact with one another and understand what the code is doing. But those are terrible types for optimization, because they are much too vague. You cannot really do anything with types like these to specialize execution to make it faster. But they did it anyway. mypyc is using Python type annotations, and with a little care allows Python code to be up to 4 times faster, which is what this tool was created for in the first place, like to compile mypy, the type checker. The type checker is now being used as part of your experience in, you know, Visual Studio Code or PyCharm or whatever else. So people want it to be as fast as possible. Like in fact, like when it wasn't, Microsoft created its own type checker just so that it could be really, you know, like that quick. Now it's less relevant because mypy is pretty quick. But at the time, like this was really something that you could only execute on the side because of its complexity. So like mypyc was immediately kind of attractive to me when I heard about it, because what it lets you do is, you know, you just take code that you already have and maybe just compile it and see what happens, you know, kind of compiled code like still behaves the same as the code that you had. So you don't need to learn another language. You don't need to look at the resulting C code to see like, you know, what you need to tweak to make it faster. You just start and see what happens. And the types that you're using are those expressive types that we talked about before. Like if you say, you know, collection of string, it'll just say, okay, fine. Like it already helps you a little, it turns out. Like it doesn't help you a lot. It doesn't map to C++ exactly, but it'll already cut some operations, cut some corners, and let things be faster. And you can use the Python ecosystem. I already complained that, you know, if you use PyX files, you cannot use you know, the type checker because it doesn't know about PyX files. It cannot really parse the functions that you have there and whatnot. But with PyX files or whatever else there, like you use the entire ecosystem of like linters, all the formatters, like everything. Like, you know, even syntax highlighting might not work for you correctly. So with mypyc, this is not a problem because you're only using Py files. They're just regular Py files. What turns out being an additional advantage for this sort of compiled code is that just programs start faster. They're smaller and they're like in one place of memory, so you can just load them much quicker than regular Python programs. Because like Python programs are so dynamic that even things like importing can be, modified by just hooking into the import system and changing its behavior. And very, very popular kind of pieces of syntax in Python, like decorators, what they actually do is they put code that is executed on import time now, because you take some function or class and change it underneath, or I don't know, register it with some single dispatch, or add it to some CLI like with click, or just specify that this is a class method or whatever. But this is import time computation now. So looking at all those, mypyc can make some of them static, and that makes programs start up faster. So like all of this brings me to just being able to adopt mypyc for programs that I've already been using before, like they were already kind of production grade, people were depending on them, and now they just, happen to be faster. So like, I'm very happy about that. And compilation is optional, which is the greatest thing about it, because I already talked about how what we want is for you to be able to use the debugger and, kind of to be able to just Control-C or use IPython notebook and whatever. So you don't have to compile if you don't want to, or maybe if the compiler is not available for your weird platform because you're using some new CPU or whatever, then you can just use the regular Python code. It's slower, but it does work. Or for development, right? Like you're just developing, running tests, like debugging. All of this works fine. And finally, you can still use the type checker, because that's literally kind of, it's kind of married. So all this is both static type safety and runtime type safety, because mypyc is able to cut, short a bunch of type checks that Cython would also do unless you instruct it that something is particular type. So mypyc also cuts those checks, but it does it by first checking on the boundary of your static code. It checks whether your list of string is really a list of strings. It will check it. And when it sees, okay, it's really a list of string, then it allows this binary code to be really fast. And it doesn't, like if it doesn't, like then it raises an exception. So you're getting a runtime type checker for free with this. So yeah, like MyPy versus Cython, I already kind of were comparing it while talking before. But the thing is, you don't need this non-standard syntax. Typing support is first class. Type inference is powerful. So you saw how in Cython I had to literally tell it that for I, whatever, I is an int32t. I had to really be very explicit about everything. Like here with mypyc, you don't have to. Like it'll see that something is a dictionary, but later on it's a dictionary where keys are strings and values are ints. So it'll do all of this for you without you having to say, all the types all the time. And as I said, like the enforcement of types at runtime is strict, which makes debugging faster as well, because you see where the problem arose, where you say it's a list of string, but there was a none at the end. So how is mypyc fast? Well, first of all, even Cython code, where you just take a literal py file, changes its extension, and give it to the Cython compiler, will do the same. It'll already be a little faster because there's no interpreter overhead. So what Python does when it sees a py file, it will translate your code to a bytecode for a stack-based interpreter, like that we have internally. And there's a really, really tight loop in cevalc that just takes an opcode, executes it, takes an opcode, executes it, and so on and so on. So by already seeing what the opcodes would execute on the C level, we can skip this loop. So we don't have to look at our list of opcodes and modify the state of this stack-based machine. We already run the C instructions that would get executed anyway. So that's already kind of like 15 to 20% faster. But then, as I said, the type checks are only made at static typing boundaries. So all code that is fully type annotated it doesn't need to be checked anymore because we checked with an actual type checker that this actually checks out, this will be safe. But on the boundary where you have some any's or something is not annotated, then you need to put type checks to ensure that the list of string is really a list of string. And then like booleans and ints are in fact unboxed, meaning they don't use the Python variants, they use the native variants, which allow them to be much faster. Like booleans, in fact, for logical code are like super abundant. I wasn't aware like how kind of boolean heavy Python code is. And attributes that you specify that they're final, so they won't be re-annotated, like reassigned later on, and same for functions and classes, are made immutable and put in a different segment of memory, meaning they load super fast. And they're close to one another, meaning they're very great for cache locality. So attributes, you would often not care about like in Python whether they're final or not, but for functions and classes, it is super unlikely unless you're mocking, so like you're writing tests and you're patching some particular function with another function. That's pretty much the only use case I have to change a function at runtime to something else. Usually you don't do it, you just use whatever you had in your layout. So if you do that, like if you just leave the functions and classes alone, they can be much faster with mypyc. And finally, name references. So the example I gave at the very start with datetime.date.today being super dynamic is not so in mypyc. This is all resolved at compile time. So when you have this line of code, what mypyc code will do, it'll directly go to the today method and call it on the object. It will not do this dance of like, oh, maybe somebody actually, hooked into it and changed it. But obviously, it would be too cool, it would be too amazing if it just worked for any kind of Python code, so it doesn't. Classes work if you use single inheritance, because otherwise you have this diamond problem and you have to do some runtime resolution to actually see what's going to happen. Because, if you register a bunch of implementations on single dispatch, you'll see sometimes that like it'll refuse to actually register another implementation because they're exactly in the same distance from the base class. So like single dispatch wouldn't know which implementation to use. So this is the same problem only at compile time, which is why mypyc requires you to use single inheritance. And classes are made into native classes which behave almost the same, but not exactly the same. What are native classes? Well, if you ever used some kind of type in Python that is implemented in C, there's plenty of them. Like, I don't know, like a lot of the built-ins, I think even datetime now like uses C implemented classes. You'll see that they kind of have a little bit of a different wrapper, and some things on them don't behave in such a native, like dynamic way as pure Python classes. Like they don't have dunder-dict. You cannot really kind of just slap like arbitrary attributes on them. It'll just tell you it doesn't have this attribute. Sort of like with slots, but they're not slots. So most meta classes, if you use those, like are not supported for mypyc compilation, because again, this is something that is happening at runtime. It takes one class and creates a different one for you. So this kind of beats the purpose of static compilation. But some meta classes are in fact supported, like the ABC ones and whatnot, because we know what the implementation of ABC does. So we generate code that literally does the same thing, only statically. But most meta classes, like user-based data classes that mypyc doesn't know about, they're not supported. And most class decorators, because the two last ones like are really the same thing. They're just expressed differently. But like you take a class and you return a different class. So most class decorators are also not supported. So in particular, data class is an exception. It is supported because it's implemented in mypyc. But for example, adders, which Hinek always kind of complains to me about, like, well, it's not. It could be added, but somebody would have to just go and add support for this to mypyc to make this kind of like custom code for it. And attributes, as I said, are slotted, like that's the consequence of being native classes. So you cannot have kind of weird initialization in your code where there is a class that has an init method that does a bunch of things, but doesn't create all fields, but only later you have some connect method or whatever else, and that method actually creates new attributes that weren't there in init. This will not work. You have to create all your attributes on your object in dunder init or on the class itself. Yeah, because there's no dict and there's no operator overloading. Like most people would be like, what? Do we have operator overloading in Python? Yes, we do, and like a bunch of libraries use them, like ORMs love them, but like most actual user code doesn't bother with it. Yeah, and no custom descriptors. What? We have those? Yeah. Yeah, so obviously like this was created, it was used for mypy, so I was like, let's add it to black. So the mypyc maintainer was like, okay, here's the pull request, let's have it. And like not even 3 years later, just 2 years later with a month, we were able to land it. So it was you know, smooth sailing. No, it wasn't. It was like a super alpha project at the moment. So like obviously we found a lot of things that had to be kind of changed and improved in both mypyc and in black to like move things around, like to make it easier for mypyc to understand what's going on. But the required changes weren't actually that drastic, like the required changes in black. So what we mostly had to do is to type everything. Like before, black was fully annotated for my code, but it wasn't for the lib223 code that we vendored from CPython. That was just left alone because it would be easier later on to contribute fixes back to CPython. Like now we had to actually type everything because mypyc wants everything typed. And it turns out that some of the types that we had were invalid. Like mypy wasn't complaining, but at runtime they were crashing because it turns out like we were a little lax about like annotating some functions. And we had to downgrade to data classes from adders, you know, such as life. And like a bunch of weird things that we had to do is like, you know, okay, we had to initialize the variables in dunder init to none or like on the level of the class or module. So most changes looked really like this, like they were like super trivial changes. Like you put a bunch of finals so that those things, accesses to those are now much faster. Or stuff like you actually had to make types correct because it wasn't correct before, but mypy wasn't complaining because both of those well have the same inheritance chain, but you know, like this difference was important for mypyc. And like all in all, like this didn't take that much work once we knew what needs to be done. Like as you can see, blib223 had to be in fact annotated, which it wasn't before. A lot of those annotations were like super easy. Like the Python symbols in lib223 are just like super dynamic. There's some getAttr thing that will just generate things for you as you come. So now we had to unwind this and actually list all the possibilities. But by doing this, this started actually, you know, working for, you know, command space in Visual Studio Code because now it knew what possibilities there are. It wasn't getAttr anymore. So like I was happy. Yeah, and finally, there was just a little kind of, well, scaffolding that we needed in setup.py to actually make mypy compile your thing. Like, because otherwise, like, how do you actually compile it? So you have to actually list the sources and invoke the compiler when supported platform was encountered. Yeah, so all of this, pretty much the same thing, like just a bunch of refactorings that we had, like with some moved initializations where we actually had to specify them in dunder init instead of just lying that they are class level variables. They're not, they're instance level. And so on and so on. Like, as you can see, this is weird, like there's still multiple inheritance here. So like, what about that? Well, in fact, like mypyc does allow for a very limited version of multiple inheritance that it calls traits, where you only have some subset of your functionality, but you don't add to the inheritance chain. So traits can be only kind of base classes, right? They cannot inherit from anything, and they cannot add to dunder init and anything else. Like, they just add a new functionality, then they work. So, you know, kind of all of this, not trivial, but pretty easy to do. And later, we got twice as fast, like, which was like kind of, I didn't expect it to be that good, but it was. So like now we ship like compiled if you are on a supported platform, which we build pretty much for everybody except for Muzzle. So if you use Alpine Linux locally somehow, like, then you won't be using fast black, you know, like otherwise, like it's fine. So what does mypyc do? It's the same thing as Cython, literally, only you're using py files instead of pyx files. So what about PyPy? Well, PyPy says that it's like 4.5 times faster than CPython, and it's also super compatible, and you can just use your Python code, and it's faster. So why don't people do it? Why don't people actually use PyPy? There are many reasons. First of all, 4 times faster is sensible, is good. It's not 100 times faster, but this is already in the ballpark of what mypyc can do with actual CPython compatible code, and this is not, right? Like, people say it's super compatible, but in fact what you have is a support matrix where there's still 2.7 that they release. You can still use PyPy that implements Python 2.7. 3.7 is not supported anymore when in CPython it still gets security patches. 3.8 is the main current branch that they are supporting right now. 3.9 is kind of beta, so well, might crash for you, but like mostly it's probably fine. And 3.10, which is already kind of old news for us, like is still like a work in progress. Like, this is not to say that like those guys are doing a bad job. Like, in fact, like I was part of their sprint like in 2019 in Düsseldorf. In fact, we're gonna be doing it again because the pandemic is over. Maybe like in September. So I'm gonna be going back like to this weird place like where it's like 30 kilometers outside of Düsseldorf is there's this like super big like factory complex that is now like gutted of the actual factory equipment and made into an art installation. So like it's a really cool place. I kind of recommend you go there. In fact, like all of those people, you know, they make awesome work on PyPy. Like that, the fact that you can have a Python interpreter written in Python is amazing. Even if you don't use PyPy, you do, because part of PyPy was PyTest. Like that is literally a project that was taken from PyPy's own code base because it was so useful for other purposes. And a lot of other code like CFFI like also just started as a PyPy feature, but now it's generally useful for anybody. And in fact, now they're working on HPy, making this Python C API better for like authors of C extensions, but also for PyPy, just it turns out. So like PyPy is great, but there's problems with it because those team members of the PyPy project will always have to catch up to whatever CPython already implemented. And it's just like a small team, as you saw. Like it's easily 10 times smaller than CPython, which now has a large team at Microsoft working on it full time. So I don't envy them. It's a hard work. So could CPython have a JIT? Well, I like to show myself on pictures to you. You know, here I am. This is the Language Summit, this PyCon US in Salt Lake City. We were in fact talking about like, hey, like what is gonna happen in 3.12 and 3.13? And it turns out that like a JIT might be coming. We in fact even have one, like a really poor man's JIT right now. Like if you read what the specializing adaptive interpreter is, it is really just taking common operations that you're doing on objects and seeing the data that you're using with it and saying, oh, you can use this other opcode instead, which is faster. So it's already kind of paving the way into like a full-blown JIT later on. Like, we already have a bunch of operations that are implemented. Like, obviously the wins of every single one of them isn't really, you know, kind of gonna blow your mind, but the sum of it looks very promising. But the thing is, like, they're saying 312, no, like we're not gonna make it, but 313, probably it's like a good bet that there's gonna be a JIT in Python. Like, me, myself, I think like maybe 314, like I'm a little more kind of conservative about this, but it's also PyPy. Yeah, you can use a JIT today. You can just install it from PyPI, this pigeon for 310. It does make things the same pretty much. Like, if you use some specific things that like Anthony implemented, like it can be like 10 times faster for you. But for most things that you do in Python, it doesn't do much. Like, it uses the current API that CPython allows you to hook into to change frame evaluation. Turns out this API sucks for JITs, so we're gonna have a new one, which is why I'm thinking 314 more than 313. Some of the things that I talked about today were independently released as a blog post by Glyph, so I didn't read his blog post and just made it into a talk. No, I already gave this talk in Lithuania, so, you know, kind of, yeah, but you should read this too, because it has a very simple end-to-end example of introducing mypyc to a very simple project. So if you're still like not sure, like how would I even do this? Like, this is the blog post to read. Like, I didn't want to do it now because I know you don't have your laptops out, you know, to actually try it out. Like, you can try it out with this blog post instead. But I'm Łukasz, I come from the internet, so you can just find me on all sorts of places here. Always happy to hear from you and like answer questions and whatnot. Thanks for having me.
Do we have any questions? But unfortunately, we have time only for 2 of them, so.
Okay, so the second one.
We skip right to the second question. Cool.
Are there any caveats when I'm using C extensions? Caveats with using mypyc?
Oh, you can use C extensions. This is one of the static typing boundaries. So when you're using C extensions with mypyc code, like what's going to happen is on the boundary of it, so on the call side, like there's going to be additional type checks. So if you have this in a tight loop, well, like it's likely going to be slower than it already was. Like, so like, you know, kind of, it depends. So for this use case, like Cython is still going to be better because Cython allows you to bind into C without this Python kind of API. Here you don't have this. Like, here actual Python code gets much faster, while interfacing with C or C++ is not the focus. Like, here, in fact, it's kind of hindering us because we need to check whether the data we got from it was the type that we told it would be with type annotations, which from C extensions is going to be some stub file, so we cannot really check whether this is correct. Like, we just assume that, you know, somebody just gave us good annotations, or maybe it's just any, so we don't know anything, and now we just have to assume.
So there's a chance that it will be slower, actually, right?
Oh yes, like parts of black code also got slower, but like others like got much faster, so like it evened out. Like, black is using async IO to like multi-process. If you like just say black dot on like CPython, like it'll reformat everything, but there's like so many files that it just uses async IO to just do it in parallel for all the CPUs that you have. So the formatting is in Python, so it's much faster, but the actual scheduling is a little slower because that's UV loop, that's async IO. But it doesn't matter in the end because, you know, kind of the bulk of the time spent is on actual formatting, which was pure Python.
So profiling. Thank you.
Oh yeah.
Question for the context. I'm a maintainer of Apache Airflow,
Cool.
as you can see, probably. Okay, Airflow is a mostly networking database,
Yeah.
mostly that. Can we get like significant performance improvements from mypyc as well? Do you think it's like it's worth trying? And is it possible to do it partially? Like, do we have to convert the whole of Airflow to mypyc, or is it possible to do it part by part, or like piece by piece?
What I focused on and mypy focused on for now is a compilation unit that becomes its own executable, right? So like Black is now just importing this big module that is all now C, but we do make this module. So if you only just kind of mypyc a bunch of your code, like a subset of your code, and still use pure Python for everything else, that'll still work. The only problem with that is that if there is a big layer of API, there's going to be a lot of type checks on the boundary of it, right? Like, so you don't want to have like too many entry points to your SO, because otherwise, like all those entry points are going to be in fact like doing checks. For a database in particular, if I said, if we get a list of string, we're in fact checking if it's a list of string. If there's 10 million strings, like we're going to be checking if there's 10 million strings. So it's not going to be very fast.
So again, profiling.
Yeah, again, profiling. But like for the client side or for CLI, like this is perfect.
Yeah. That's what I was thinking about.
Okay, cool.